So here we're going to look at the predicate logic section. So a predicate's like this, right? So before we talked about propositions, now we're going to have a sentence, but it's actually going to contain variables. Now this is much more like what we do in actual English, right? So this sentence might be X is four-legged, right? I have a cat sitting next to me, so so that might be our sentence right there, right? So what this is it's something where when I put something in there for that variable, like Tally, right? So that's the name of my cat. So Tally is four-legged, right? Then that becomes a true proposition, right? So when we take a value that could go in for the variable and we substitute it in there, then what we get is now a proposition. So it's got to be something that's true or false, right? Now, one thing about this kind of structure is we need to have some sort of domain over which X is ranging, right? So that's sort of a basic thing when we're doing predicate logic. So if we're doing math, we're very often considering like statements over the real numbers or something like that, right? So or Z, right? So we might have our domain being Z. Let me do two examples here. So Z is like, dot, 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 and then -2, -1, 0, 1, 2, forever, dot, 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 right? All of the integers, right? And of course, R, just to introduce the notation, these are the real numbers, right? Reals. Q, right, is the rationals. So these are like P over Q, right? Where Q is not 0, right? Okay, so those kind of things, right? And so like some statements. So here's a statement. So first of all, well, okay, here's just a simple statement like x plus y equals z, right? This could be s of x, y, z, right? That could be a predicate, right? And so it's true in some places and it's not true in other places, right? So actually, maybe a more interesting example would be this, right? So x squared plus y squared equals z squared, right? So in this case, you know that if we interpret this sentence here over the reals, right, and we put in a value for z, right, if I look at the set of x squared plus y squared equals, I'll call, instead of calling z, I'll call it r squared. Let's say r is a specific element of the reals, right? Then what we have here is a circle, right? So you know sort of graphically how to express the set of places where this is true, right, for a specific R, right? So like the unit circle is the set of x, y, such that SXY1 holds, right? Things like that. On the other hand, if you look at x squared plus y squared equals r squared, or even z squared in general, right? So let's put the z back in there as a variable for x, y, and z in the integers, right? Then, well, that becomes a trickier problem, right? So we're saying, are there, for what integers is it true that x squared plus y squared equals z squared, right? And so it's kind of a famous problem, and they're called Pythagorean triples, right? So the integers for which that's true are Pythagorean triples, right? And you might ask something like this: when is it the case that x cubed plus y cubed equals z cubed, right? For x, y, and z in the integers. And then it turns out that for x and y distinct, or let's say maybe I got to remember. So certainly I could put in 0, 0, 0, right? So that can happen, right? I can put in like 1 minus 1, 0, right? So maybe I want to restrict these to positive integers. So I'm saying something interesting here. So let's say an n, right? So n is the natural numbers, and so that's 0, 1. So it's like the non-negative integers, right? Well, then this becomes one case of Fermat's last theorem, right? So there are no solutions, right, to this thing here. At least not if x and y, or maybe, okay, fine. So let's take out 0, right? So anyway, if you look at just positive, right, integers, there's no solutions to this thing, right? I mean, I want to avoid something stupid like 0 plus 0 equals 0, right? And so that's clearly a solution, but there's no other ones, right? So where you're working, right? The domain you're working in definitely affects when a particular predicate is true or false, right? So that's something to keep in mind. Um, let's see. The next thing to look at here are quantifiers. So I'm going to look at one that's maybe not the simplest thing in the world, but one that maybe is familiar. So we love to torture students with this and say that, the limit as x approaches a of f of x equals L, for example, right? So where are the like actual variables that, like, what is this a in terms of predicates, right? What are the variables here? So it's really S of so here we have to be a little bit careful, right? So the place we're working on is some place where we can do calculus, right? So probably the reals, maybe the complex numbers, something like that. So let's say that the reals are where we're looking at, right? And this is a sentence about A and L, because those are the real numbers that are changing here. F is like part of the given thing, right? So it's like a sentence about F, right? Um, in the reals A and L. And so we may ask now, for what A and what L are these true? So when is it true that as x approaches A, right, f of x approaches L, right? So that would be this kind of thing. Now this sentence can be expressed in a much more, the way we actually, okay, so what does it actually mean to say you have a limit? So here's what it means, and I'm going to write it all out with these things called quantifiers. So it means that for all epsilon, so this upside down A is written for all, and we say greater than 0, right? There exists a delta greater than 0, right? Such that for all x, right, if x is, well, now put some parentheses. So again, you might put parentheses around various parts here just to make sure right? So for all x, if 0 is less than x minus a, right, is less than epsilon, is less than delta, right? Okay, then, right, so here's our if then thing, right? So that's like the hypothesis, or the hypothesis here. Then, right, f of x minus L, right, is less than epsilon, right? So there we go. Big complicated sentence, right? Um, so, and this is what makes it hard, right? I mean, what makes this sentence hard? I mean, what actually does make this hard for students? What makes it hard for students is this switching of quantifiers up here, right? So it goes for all, there exist for all, right? So this is where the quantifiers switch from for all to there exist to for all, right? When you have this kind of thing like that, this adds complexity into whatever it is you're trying to do. So just to be clear, let me just write this out so we have it once. So for all x, sx, right, means, for all x, right, s holds at x, right? So that's what it means. And there exist x, sx means, there exist x, such that, s, I'm getting my s's and f's mixed up, so sx, right? So for all and there exist are these quantifiers right here. Okay. How would you, just to dwell on this for a second. So if I have something like, for all x, there exists y, such that s, x, y happens, right? You can almost think of this as a game. Like if player one plays an x, player one plays an x, player two has to be able to answer with a y, so two has to be able to respond with a y, right? And if that happens, then, like, player two wins, so to speak, right? But the point is, you have to consider all possible x's, come up with some y, right? So that's a tricky thing, right? It might be a tricky thing to do, right? So this is what makes proving, epsilon delta proofs in calculus hard. You have to do that, right? Given any epsilon at all, I have to come up with some delta, and usually you find some sort of rule, some sort of function, right? So that's another thing you might have here, right? You might say, well, this would hold if and only if there's some sort of, there is some function f, right, such that for all x, s of x and f of x, right? So it's sort of handing you the y, right? That you don't have to have a function like that, right? So it becomes kind of tricky. I mean, sometimes you can produce a thing exactly, right? You know exactly what it is. Sometimes you can just show that something exists without actually knowing what it is, right? So we'll see examples of these things when we actually get to doing proofs. Usually when you're doing an epsilon delta proof, you say, given an arbitrary epsilon, I have some sort of way of producing, right, as a function of, like, it's almost like delta of epsilon, right, that's going to work for this kind of argument. But this is what makes things complicated, right? And this is what predicate logic is. I mean, you have the usual and, ors, you know, negations, all that stuff, but you have these additional quantifiers. That's the thing. That's the thing that adds complexity. So, I mean, another thing is that, you know, in the propositional calculus, right, if you want to know something satisfied or not, you know, you have a sentence, and you just want to know, do I have something that satisfies the sentence? You just need to come up with T's and F's, right, that satisfy the sentence. If you have something here in predicate logic, again, I'll just write this one down again. If you have this, you know, equals z cubed, right, and you're restricting to, you know, to the set 1, 2, etc., right? Okay. Is there anything there, right? Is this satisfiable? Can you find an X, Y, and Z in this set that actually satisfy this? And it's incredibly hard to prove, right? I mean, it was just proved relatively recently after, you know, hundreds of years, and the proof is, you know, 800 pages long. So it's a big change. It's a big jump when you go from propositional calculus to predicate calculus, and you want to know, can I satisfy a sentence, right? It becomes much more complicated. Just real quickly, a little bit about the sort of like some things, like we have these equivalences. So let me actually not keep scrolling, but let me just erase this. There are some, you know, there are many rules, right? And so I certainly won't talk about them all, but like um, uh, one of them would be like so remember De Morgan's rule was like this, not A or B. In one of the versions, right, is not A and not B, right? So here we have a corresponding thing for existential quantifiers, right? So not there exist X, some sentence phi of X, right, is going to be equivalent to for all X, not phi of X, right? So these are equivalent, right? So I could if I'm in the middle of an argument and I'm seeing that, I could always replace it with that. Similarly, we had the not A and B is equivalent to not A or not B, right? And so this is going to change over here to not for all X, phi X, right? So for all is kind of like and, right? It has to hold everywhere, right? And or is kind of like, you know, there exists, right? There's something, right? One of those cases holds, right? So this is going to be equivalent to there exists X, not phi X, right? So these rules here are like, you know, rules of, you know, where we're saying two things are equivalent. So if you were doing like laying out all the axioms, right, for prepositional calculus, these would be like things you would throw into your axioms there. Also, you have rules that allow you to, you have modus potens, modus tollens, all those kind of things, but you have rules that specifically for quantifiers. So we have rules like this. If I have there exist X phi X, right, I can deduce, and so I could just write it like this. I'll write it two different ways. I can deduce phi of A, right, for some A, right? Now I may not know what that A is, but I can just say there's some A such that phi of A holds, right? So in the middle of my proof, I just say there's some A there, right? So I might write it like this. I might write it like this. Sometimes we write it, you know, like this is like it's very useful to think of proofs as like these tree-like structures. And so there I would be going kind of down this tree. This is called instantiation because we're taking a quantifier and we're instantiating it with a specific named object in there. But here we do have to make sure we say, for sum a, right? There's also a similar one for, if I have for all x phi of x in my argument, I can say phi of a for all a. Okay. So I'll give you an example in a minute where we use some of this, specifically some things like that. But both of these are called instantiation because I'm taking the quantified thing with a quantifier here and I'm replacing it with an unquantified formula and putting a specific a in there, right? So same thing there. And you can go the other way around too, right? So if you've proved somehow that for all a, phi a holds, right? Then you can deduce for all x phi x, right? And if you've proved that phi of a holds for any a, right? Then you can deduce there exists an x phi x, right? And so these are called generalization because you're going from specific cases to these general quantified cases, right? So those are called generalizations. Let's do a little example. I don't want to get it. I mean, this can become really, really complicated. So I don't want to do that. But let me just do sort of a nice, simple example. How would we kind of axiomatize what an order is, right? So I have some set of objects. I'll just say A. I mean, we're going to talk about set theory in a minute, but let's just say I have some set. Okay, so let's be vague about it for a second. I'm going to have some axioms on this set. It's going to say things like R x y implies not, well, let's see, Rxy, let's be a little bit careful here, and x not equal to y implies not Ryx, okay? And it's going to say Rxy, maybe you can even guess what's going to happen here, and YZ. Actually, this is a good example because I'm doing something else that I need to say something about. Implies RXZ, right? And so this is like transitivity, right? You kind of see that XY, YZ, XZ, right? And let's see, I want maybe this one R. So let's see, I want one like this. Yeah, okay, yeah, I guess I want this. I want RXY or RYX or X equals Y, right? So that's like a trichotomy. Maybe you guys can see what's going on here. So one thing I'm doing here is I'm writing these X's and Y's without saying exactly what they are. That's because when we write stuff like this in math, we're really implicitly saying for all X, for all Y, that, right? And same here, for all X, for all Y. Whoops. Sorry, for all X, for all Y, for all Z, right? I need a third one. I've got some buttons on the side of my thing I keep hitting over here. For all X, for all Y, for all Z, right? Because that had 3 variables. Here we have again for all X, for all Y, right? So when we don't write these and we're laying out kind of a definition or axioms, here I'm kind of giving you a definition of something. Those are implicit, right? So those are implicit. And these rules like this are called universal because their quantifiers are all out front and all universal quantifiers. And they're really important when you're doing algebra because most axioms for algebra are universal rules like that. Like, I mean, just for an example, like A plus B, plus C equals A plus B plus C, right? So that's associativity. That's the associativity law. What that really you need to write for all A, for all B, for all C, that thing holds, right? But rules of algebra tend to be like this, right? There's a few rules that are not like this, like there exists a 0, right? Such that x plus 0 equals 0 plus x equals x, right? For all, sorry, there exists, and here I have left out 1, so let's, yep. Okay, so it's like there exists something such that for all x, right? So that would be like there's a additive identity, right? So the existence of additive identities or multiplicative identities comes up a lot as existence things, but the rest of the axioms tend to be universal. And this actually turns out to be really important when you're doing some of your math. Let me erase that and go back to the one I was looking at. So I've got these axioms up here, and you might kind of look at those and say, oh, this looks like an ordering, right? Let's see, do I want one more? I want to say one more thing. So let me add one more to it. I want to say, whoops. Okay, I want to say for all x, there exists a y such that r x y. So I'm going to add that one rule to it. So this is actually saying something about existence, right? So like a model of this thing might be like the integers, right? So and where r is less than, right? So this is kind of capturing the idea of less than, right? So x is less than y, and x not equal to y means y is not less than x, right? So that makes sense. X is less than y and y is less than z, then x is less than z, right? X is less than y. So for every pair x and y, either x is less than y or y is less than x or x equals y, right? So the only kind of sets that would model this would be something that look like orders, right? They'd have to have points, they'd have to be related by r, in between those points, right? And this one here says I can always find, for everything, I can always find a bigger thing, right? So a model for this might be like the natural numbers, it might be the integers, right? Or it might even be Q, right? So that's fine. I mean, they don't have to be discrete like this. Or the reals, right? But it's got to be some sort of like linearly ordered thing. That's kind of an intuition. We're not proving that exactly. But what I do want to do, right, is I want to actually go through like a little proof from these axioms. Actually, let me select these and shrink them a little bit. Okay, and I want to like make them smaller, put them up here. So there's kind of our axioms we're working with. And I want to show from these axioms that I can find four things, right? So I want to prove, so prove there exist x, actually four maybe is too much. Let's get three. So x1, x2. By the way, when I write several variables like this, I'm really just shortening. There exists x1, there exists x2, there exists x3, such that r x1 um, x2 and r x2 x3. So I've got at least three things, right, in order. Okay. I guess even to get started, I'm gonna have to say there's something, right? So there exists an x such that x equals x. I gotta just say there is something, right? I can't have the empty set being my a, right? So let's add that to our axioms, right? Okay, so I just want to go through the kind of like how would you use like the formal sort of proof. So here are my assumptions up here, and I want to get to that sentence right there, right? So I get to say there exists an x such that x equals x, right? That's a given. Okay, and from that I get to say a equals a for some a. That is instantiation, right? So this is that rule where I'm going from there exists something to a specific example for some a, right? And then I want to say, okay, so I have that I have this one right here for all x. There exists a y such that r of xy, right? So I have that as one of my axioms, right? So this is a given again. And this is kind of like a game, right? I mean, you really should kind of know this game. And I'm going to use instantiation again. So I'm going to get there exists an x, r, sorry, there for all x there exists a y. Sorry, there exists a y such that r of a y, right? Now, why did I get to do that? Well, I'm using that universal instantiation, right? And that's true for all a. So in particular, it's true for that a that I have there. I don't know what that a is, right? I don't have any specific set in mind, but for whatever that one was that was given to me by that instantiation, I get to get rid of this universal quantifier and put that one in there, right? And so then I get to say, well, r of a b for some b. And I think you probably see how to keep doing this now, right? So now I've got that, right? Um, I know A doesn't equal to B, right? Um, because let's see, where did I actually put that? I guess if A equals B, then R of I guess this would be, if if A equals B, then R of AB would imply R of BA, right? Because A and B would be the same thing, right? So A doesn't equal B. So I'm actually using some logic of equality too there, right? But this A and B are now two different things, right? Now I can kind of repeat these steps here, right, and get out a B, right? So I sort of repeat that, or get out a C, right? So I say, well, let me just repeat it. We don't want to skip anything here. So again, I refer to this one, right? So again, I say for all x, there exists a y, r of x, y. Again, that was a given, right? So now I can replace the x with a b. That's the instantiation again. So I get there exists y, r of b, y, right? That's instantiation. And then I get to instantiate again and say r of b, c for some c, right? And then so now I have R of AB and I have R of BC, right? Um, so I do know that R of AC, for example, I know that that would come from from another one of our rules up there. But what I'm really interested in here is just this. I know I can put those together in a conjunction, right? That was one of my propositional things I could do. So I have this and I have that, so I can derive this. Um, and I think we just called it rule conjunction. Right? And then once I have this, right, I can start using generalizations, and I can say there exists an x such that R of xb and R of bc, right? So I can do that, right? And then so now I'm using the generalization, right? I'm going from a specific a to a there exists an x, right? And I can do there exists an x, and I can do it again, right? There exists a y, right? Such that R of x, y, and R of y, c, right? And so I can do it one more time and get there exists a z, there exists a y, there exists an x, right? Such that R of x, y, and R of y, z, right? And I think if that's not what I wanted to prove, that's what I meant to say I wanted to prove. So we get the thing that we were after. But we used various places generalization and various places instantiation, right? And that was the main thing I wanted to show. That's the way you kind of use this stuff. And you really do, even if you're not writing down things formally like this, you really do this kind of stuff all the time when you're doing math, right? I mean, just all the time. Like if we're doing one of those epsilon delta proofs, right? We say, let epsilon be greater than 0. Well, can we do that? Well, that's just arbitrary epsilon greater than 0, right? That's the universal instantiation, right? And then you say that then you've got to find delta such that blah blah blah, right? But very often you start with something like let something be something, and that's using that instantiation. And then later on we say since epsilon was arbitrary, we can say for all epsilon greater than 0, right? And that's using the generalization, right? Because this is an arbitrary epsilon. So you really do use those kind of under the hood all the time when you're doing math proofs. Okay, let's come back in a minute and do the set theory bit.